Ethernet frame and IP packet. An IP packet, layer 3, carries logical addressing, IP addresses, for routing across networks, while an Ethernet frame, layer 2, is the physical container that carries the IP packet across a local network segment, adding physical addressing, MAC addresses, and error-checking information, essentially wrapping the packet for its local hop delivery. Think of the IP packet as a letter with an address, and the Ethernet frame as the mailing envelope with local delivery instructions, like the mail carrier's route, added by the postal service. IP packet, network layer, layer 3, purpose, handles logical addressing, IP addresses, and routing data between different networks. Contents, contains source/destination IP addresses, time to live, TTL, and other network-specific info. Analogy, the actual letter with the final destination address. Ethernet frame, data link layer, layer 2, purpose, delivers data across a single local network segment using physical addresses. Contents, adds an Ethernet header, source/destination MAC addresses, ether type, and a trailer, frame check sequence for error detection, around the IP packet. Analogy, the envelope or box that gets the letter from one post office, router, to the next. The relationship, encapsulation 1. Data to segment, data from applications gets a TCP/UDP header, transport layer. 2 segment to packet, the IP header, with IP addresses, is added, creating an IP packet. 3 packet to frame, the IP packet becomes the payload, data, of the Ethernet frame, which gets its own header, MAC addresses, and trailer. 4 transmission, the Ethernet frame is sent over the physical medium, layer 1. 5 to encapsulation, at the destination, the frame is stripped off, revealing the IP packet, which is then processed to reveal the original data. OSI model layers. The primary distinction lies in which layer of the OSI model each unit operates at. Ethernet frames are the protocol data unit, PDU, of the data link layer, layer 2. This layer is responsible for physical addressing and reliable transmission within a single local network segment. IP packets are the PDU of the network layer, layer 3. This layer handles logical addressing, IP addresses, and routing of data across multiple, interconnected networks, the Internet. Key differences in function and addressing feature: Ethernet frame, IP packet, OSI layer, data link layer, layer 2, network layer, layer 3, addressing uses physical MAC addresses, uses logical IP addresses, local network, point-to-point link or LAN scope, end-to-end across the entire Internet segment, device use switches, read and forward frames, routers, read and forward packets, encapsulates the TCP segment or UDP, encapsulation encapsulates the IP packet datagram. The encapsulation process: when data is sent from a computer, one higher layer data is passed down to the network layer and becomes an IP packet with a source and destination IP address. This IP address identifies the source and final destination host globally. 2. The IP packet is then passed down to the data link layer, where it is wrapped with an Ethernet header and trailer, forming a complete Ethernet frame. 3. The Ethernet header contains the source and destination MAC addresses needed to deliver the frame to the next device on the local network, example a switch or router. 4. Once the frame reaches a router, the router removes the Ethernet header and trailer to inspect the IP packet's destination IP address. It then determines the next hop and encapsulates the original IP packet within a new Ethernet frame, with different source and destination MAC addresses, for the next network segment. This process repeats at each hop until the packet reaches its final destination. Ethernet frame structure: an Ethernet frame is the data link layer, layer 2, protocol data unit, PDU, that carries data over a physical network link. It has a minimum size of 64 bytes and a maximum of 1518 bytes, excluding the preamble and start frame delimiter, or SFD. The core fields of an Ethernet frame are: field size, bytes, description, preamble, 7 alternating ones and zeros for receiver synchronization. Start frame: a specific bit pattern, 10101011, that signals the start of the actual one delimiter, SFD, frame. Destination MAC: the physical, MAC, address of the receiving device on the local 6 address network. Source MAC: 6, the physical, MAC, address of the sending device. Address 2 indicates either the length of the data field, if value equals 1500, or the ether type of higher layer protocol, if value equals 1536, such as IPv4 length, 0x0800, or IPv6, 0x86DD. Contains the encapsulated data from the upper layer, example an IP payload, data and variable packet. Padding is added if the data is less than the minimum 46 pad, 46 to 1500, bytes to ensure proper collision detection. Frame check: for a 32-bit cyclic redundancy check, CRC, used for error detection. Sequence, FCS. IPv4 header structure: the IP header is the network layer, layer 3, control information at the beginning of an IP packet, or datagram. Its primary function is to provide logical addressing and routing across networks. The minimum header size is 20 bytes, but it can be up to 60 bytes if optional fields are used. Size field description, bits, bytes, version 40.5 indicates the IP version, which is 4 for IPv4. Internet header, the length of the IP header in 32-bit words, minimum 40.5 length, IHL, 5, maximum 15. Type of service used for quality of service, QoS, allowing packets to 81, TOS/DSCP be prioritized. The entire size of the IP packet, header plus payload, in total length 16.2 bytes. A unique ID used to help reassemble fragmented identification 16.2 packets. Control bits for fragmentation, example don't fragment, flags 3 more fragments. Indicates the position of a fragment within the original fragment offset 13 unfragmented packet. A hop counter, decremented by each router, that time to live, TTL, 81 prevents packets from looping infinitely. Identifies the encapsulated transport layer protocol 81, example TCP equals 6, UDP equals 17, ICMP equals 1. An error detecting code for the header only, header checksum 16.2 recomputed at each hop. Source IP address 32 for the 32-bit IP address of the sending device. Destination IP address 32 for the 32-bit IP address of the intended recipient device. Optional fields used for testing or special routing options variable, rarely used in practice. Added to ensure the options field ends on a 32-bit padding variable boundary. The IPv6 packet is composed of a 40-byte base header and, optionally, one or more extension headers. This design simplifies core routing processes and moves optional functionality to the extension headers, improving performance over IPv4. IPv6 fixed header structure. The base IPv6 header is always 40 bytes long and contains essential routing and delivery information. Size field description, bits, bytes, version 40.5. The IP version number, which is always 6. Used for quality of service, QoS, similar to the IPv4 TOS field, to traffic class 81 prioritize packets, example for real-time video. A new field that helps routers identify packets belonging to the same flow labeled 22.5 flow, a sequence of packets between a source and destination, for consistent handling, reducing reordering issues. Payload. The length of the IPv6 payload in bytes, which includes any 16.2 length extension headers and the upper layer data. Identifies the type of the first extension header, or the upper layer next header 81 protocol, like TCP or UDP, if no extension headers are present. Functions like IPv4's time to live, TTL. It is decremented by one hop limit 81 at each hop, router. If it reaches 0, the packet is discarded to prevent infinite loop. Source 128.16. The 128-bit IPv6 address of the packet's originator. Address destination 128.16. The 128-bit IPv6 address of the intended recipient. Address IPv6 extension headers, as IPv6 uses extension headers for optional information, which keeps the base header efficient for high-speed routing. These headers are chained together using the next header field in a linked list manner, with each EP pointing to the next one, until the final header points to the upper layer protocol, TCP, UDP, etc. Common extension headers include, hop-by-hop options header, contains information that must be examined by every router along the path. Routing header, allows the source to specify a specific path or list of intermediate routers the packet must traverse. Fragment header, used by the source to fragment packets that are larger than the network path's maximum transmission unit, MTU, as routers in IPv6 do not perform fragmentation. Authentication header, AUT, and encapsulating security payload, ESP, part of the IPsec framework, providing authentication, integrity, and confidentiality. Destination options header, carries information only intended for the final destination, S. Protocol field in the IPv4 header. The protocol field in the IPv4 header is an 8-bit field that specifies the type of data, payload, immediately following the IP header. It acts as a demultiplexing key, allowing the receiving host's network layer to determine which higher layer protocol, typically a transport layer protocol, should process the encapsulated data. Function and purpose demultiplexing. When an IP packet arrives at the destination host, the IP layer examines the protocol field. Based on the numerical value in this field, it passes the data portion of the packet to the correct transport layer protocol handler within the operating system's network stack. Protocol chain. This field creates a protocol chain. The Ethernet header's ether-type field points to the layer 3 protocol, IPv4, and the IPv4 header's protocol field points to the layer 4 protocol, TCP, UDP, etc., ensuring the data reaches the correct service. Packet filtering. Network administrators can use this field in configurations, such as access lists or firewall rules, to filter traffic based on the specific application or protocol being used. Common Protocol Field Values. The Internet Assigned Numbers Authority, IANA, maintains an official list of assigned protocol numbers. The most common values are decimal protocol, protocol name value, keyword 1, ICMP, Internet Control Message Protocol, used for network diagnostics like ping, transmission control protocol, connection-oriented, reliable. 6 TCP communication, 17 UDP user datagram protocol, connectionless, less overhead. 89 OSPF, open shortest path first, a routing protocol. 132 SCTP, stream control transmission protocol. Other protocols that operate directly over IP, such as IGMP, Internet Group Management Protocol. Value 2, NI Group, Enhanced Interior Gateway Routing Protocol, value 88, also have assigned protocol numbers. This mechanism is generalized in IPv6 as the next header field, which serves the identical purpose for the base header and extension headers.